3.4, writing fractions in lowest terms, which also can be said as simplifying fractions as well. It's the same thing. Now, we did talk just a little bit about simplifying fractions in the last lesson, I believe it was, where we used the circles. I think it was the circle one, where we looked at a circle. Let's see if I can do this correctly. So we had a circle, I don't know, something like this. And then if I recall correctly, I'm not going to divide it up as much, but it was, we'll say we're going to split this one up into 4 equal parts, and we'll assume that I split that up into 4 equal parts. And then what did they do? They colored in 2 of the slices of the circle, like this. And yeah, staying within the lines is not my forte, but this will work, right? Now, when we wrote the fractions for this last class, what we said was that as a fraction, you have 2 pieces that are shaded out of the 4 total pieces. But as I recall correctly, we looked at green as well. Some of you perhaps saw this like we would in green here, where really there wouldn't be a black line right here. And so you would say, well, now, and it has the same value, right? It's not like we've really changed the value of what we're looking at, but we just changed the way that we look at the fraction. So we would say now we're looking at 1 piece that's shaded in purple there out of 2 pieces. All right. So this is reduced. 1 over 2, which is 1/2, is considered the reduced form or the simplified form of 2/4, among other fractions, by the way. There's many other fractions which we could show that have the same value of 1/2, but 1/2 is its reduced, most simplified form of all of those other fractions. Okay, which really just means that we could continue splitting this circle up into lots of other different types of looking sections. Okay, so even though, and we did talk about this last time as well, even though fractions may look different, such as this 2 over 4, 2 pieces out of 4, they have the same value, such as this one, 1 piece out of 2 pieces as well. Okay? But the idea with simplification is to reduce these into numbers that can no longer be simplified. And we'll talk about those types of rules here. All right, the numerator tells us how many parts there are. The denominator tells us how big or how many parts make a whole. So I think this may have actually been the actual example we saw last time. But what fraction of the circle is shaded blue, which in this case we would say is unsimplified. So we're looking for a numerator and denominator. And the numerator would be how many pieces actually are shaded blue. So that would be 1, 2, 3, 4 pieces. And I'll reiterate this even though we did talk about this just a little bit last time. But since these pieces are all the same size and we've split them up, another word which would be appropriately used could be they've been divided, which is why fraction lines are also division. So that's 4 pieces out of 8 pieces, right? If you continue counting around here, 5, 6, 7, and 8 right there. So there's 8 total pieces. 4 of them are shaded. So that is the fraction of the circle that is shaded blue. All right, but we need now the simplified fraction of the circle, which is shaded blue. Fully simplified, by the way. Okay. Now I'm going to use the model on this, just a circle there, instead of the mathematics to do this. Okay. Now, if you hate using the model method, just understand that the mathematics way is coming, and we're going to go over it in this lesson. All right. So just like I showed in that last example, if you look at the full circle here, we can see if we just cut this directly horizontally like this, and again it would be like we're ignoring how it's been split up, but the green line right here is how we would actually look at it split up. Well, now you would have 1 piece out of 2 pieces that have shading on that one. Okay, so this I didn't know this was going to come out as 1/2 on this one, but it's still a good example, still appropriate to use this one. Because originally this was 4 pieces out of 8 that were shaded blue, but also we could say that instead of 4 out of 8, we combine the full pieces as we have it, all 4 of those blue pieces into 1 full piece, and that came out evenly with the other piece. Then so that would be one piece out of two pieces. So 1/2 would be the simplified form of that fraction 4/8, just like it was for 2/4. Of course, like I've said, this is just a visual check, right? We're just looking at this visually right now, but it's leading up to something that we can apply more with the actual mathematics, which you may or may not realize is related to the picture, but uh, it is essentially. All right, the excuse me, the what fraction of the circle is shaded blue on this one? Well, for me, if I were to count the blue pieces on that circle, I would see there's one piece that is shaded, so that'd be my numerator. Then I would just count all the pieces to figure out my denominator, right? 1, 2, 3, 4, 5, and 6. 6 total pieces, so I have 1 out of 6 pieces shaded. So as a fraction, I have 1/6. But what is the simplified fraction of the circle that is shaded blue? And yeah, I think we saw this particular example in the last lesson as well. The difference on this one, though, is when I want to simplify this fraction, I can't actually make these numbers any smaller than they are. Particularly, I mean, 1 should be a pretty obvious value that cannot be simplified any further. So where we see the 1/6 right there, um, I need to keep this as 1/6. And again, that's just looking at the fraction. But if we look at the model here as well, I can't combine this piece with any other pieces to make bigger pieces, okay? I would need more shading in order to do that. So as it turns out, 1/6, while it is the fraction that is shaded blue, it is also simultaneously the simplified fraction for this particular circle. So we've already talked about this fraction can be written in different ways without changing the value, but we can find equal value fractions by multiplying or dividing, and we have an asterisk with the division there, the numerator and the denominator by the same value. It has to be for both, okay? And be aware of this. Sometimes students will say when we scale these fractions, and I talked about scaling in the last lesson. Scaling can go up or down, but when we scale fractions, it's important to know that we're scaling them by the same value in the numerator and denominator. So just be aware. Sometimes when students look at fractions, and I'll use an example that we've seen already, like 1/2. If I scaled it up into 4/8, again they have equal value on this, so I can put an equal sign between the two. But sometimes students would just say, look, you take 1/2 and multiply it by 4. Okay, well, I mean, that's only partially true because it's not that you're multiplying the whole fraction by 4. You'd have to multiply the numerator by 4 and then the denominator as well by 4. And we can see in the numerator I got 4 times 1, which is 4. And in the denominator I have 4 times 2, which is 8. And that gives me an equivalent fraction. Now, there's reasons why this works. I'm not going to go into the reasons right now. It has to do with the identity property, right? The identity, if you multiply by 1, you get the same value back. That's essentially what I did right here, even though I'm not telling you specifically why. I'm not telling you specifically because in the past, when I've explained it, it's actually caused more confusion. So I'm going to avoid it for now. But just understand, once again, if you multiply the numerator by value, you'd have to multiply the denominator by exactly the same value. Now this one, though, I scaled it up, right? I made the two values bigger. 1 became 4, 2 became 8. But it's possible to reduce or make the numbers smaller as well. So if I looked at another example, let's see. I will use 4/10. Looks pretty good. If you wanted to scale a fraction down, which is what simplification is, then you have to not only divide the numerator by a specific value, but you have to divide the denominator by the same value. Because, and think about this too, division is going to make these numbers smaller, which is why we're using the terminology of reduced or lower terms. Okay? So on this one, I would say I could divide these both by 2. They're both even numbers, so they are divisible by 2. which when I do that, it gives me a lower, more simplified fraction, which in this case is 2/5, which also happens to turn out to be the fully simplified form of 4/10. But again, I'm just pointing out that whatever you do to the numerator or denominator, you must do to the opposite, the numerator or denominator. Okay, you have to do it to both. You can't do these differently. Like I can't say, well, I'll divide the 4 by 2, but conveniently I'll just divide the denominator by 3. Okay, you cannot do that. You cannot do that. It needs to be the same value both in the numerator and denominator. So that should bring up some questions in your mind about, well, how do we know if we are multiplying or dividing? And while I did explain that, I'm going to reiterate it though. If we're simplifying, which is what we should want, and yes, this is not saying to simplify the fraction, even though it is in different words. We want the fraction written in lowest terms. Okay, if it wants simplification or lower terms, you have to use one of those two operations, either multiplication or division. Notice we did not talk about addition or subtraction, right? It only works with multiplication or division. Since this is asking for lower terms, only multiplication or division will make the numbers smaller or lower. And division is the only one of those two that will do that, okay? And again, just like I explained in that last slide, if you wanted bigger numbers for some reason, then you would be looking at multiplication, right? So on this example, I know I need to use division, okay? The question is, what do I divide by? Now these two numbers would be nice if we had our multiplication tables memorized. And I hope some of you are getting those down, right, as you continue to study that. I know we went over that in Module 2, which actually kind of feels like it was, it's a couple weeks ago, but it feels like it was a little while ago. But as you continue to memorize those, this kind of stuff not only becomes easy and convenient, but quick as well. But it becomes more doable as well. Okay, so when we look at 24 and 32, you should be thinking, well, is that a specific multiple of values? And just so you understand as well, like if you're thinking about that, we don't really need to do this in one step. Okay. So what that also means is that you could use divisibility rules. Okay. Now, since we've more recently gone over divisibility rules, which still has to do with multiples, I'm gonna apply divisibility rules. Okay, so I would start first with 2's, right? I would say, well, are these two numbers divisible by 2? Well, the only way to make that determination is visually looking at the ones place values. I don't care about the tens place values for either of these numbers. In the ones place value, I have a 4 and a 2, which are even numbers, or you could say they're multiples of 2 as well, which means that these two numbers are also divisible by 2. And when I do that, I will have a fraction that is in lower terms. Will it be the lowest terms? I don't know, but we're going to find out. Now, of course, since I chose to divide by 2, I'm actually going to have to do the division here. So 24 divided by 2, 2 goes into 2 once. 1 times 2 is 2, subtract, that zeroes out. So I'm going to drop the 4 in the ones place value. 2 goes into 4 2 times. 2 times 2 is 4, so that's going to zero out as well. Okay? So that's my numerator. I divided the 24 by 2, and I get a quotient of 12. But I also need to do it with 32 right here, right? Divide 32 by 2. So 2 will go into 3 once. 1 times 2 is 2. This one will have a 1 remaining from the tens. Drop this 2 in the ones. 2 will go into 12 6 times. Yeah, that'll cancel out the 12 right there. So 0 remaining. So now I have 12 over 16. So by doing it with this method, I do have to double check whatever I get from the first reduction or however many reductions we get just to see if it can be further simplified. And so I look at this as 12 over 16 now and think, well, can I further simplify this? And I would start the divisibility rules again, 2. Are these numbers divisible by 2? Well, I look in the ones place value again. I see a 2 and a 6, both of which are even, which means that these two numbers, 12 and 16, are also divisible by 2. Well, these numbers are low enough, and I think I'm going to skip the long division on this just to save time. But again, these numbers are low enough where we should know what multiples these are of 2. 12 divided by 2 is 6, and 16 divided by 2 is 8. Okay, so now we're down to single-digit numbers, right? We reduced 24 and 32, 24 over 32 into 12 over 16, which we then reduced into 6 over 8. And again, these three fractions right now that we have, they are all equivalent. They're all the same value. But are 6 and 8 divisible by any of the same things as well? Yeah, this is a rare situation where we divided by 2 and then we were able to divide by 2 again, but we're always reapplying our divisibility rules, right? So I got the 12 over 16, and then I checked to see, well, are those divisible by 2 again? They just happen to be the same on this one. So, it is possible that they could be divisible by other numbers, such as 3, 5, 10, 7, and so forth. But right now, I'm just kind of looking at, again, this is our basic divisibility rule. So you're always reapplying those, but yeah, it's not always going to be that you're going to divide by 2 and then suddenly you can automatically divide by 2. Yep. So yeah, and that's why I'm reapplying now my divisibility rules to 6 and 8. Well, 6 and 8 are both even numbers, which means that they are also divisible by 2. So I would look at this new fraction, 6 divided by 6 over 8, and divide each by 2. 6 divided by 2 is 3. 8 divided by 2 is 4. Okay, so again, these are even lower numbers now. They're lower numbers, 3 over 4. But is that as far as we can take this in terms of simplification? So now the numbers are not both even anymore, and that's okay. But we can only go as high as, excuse me, I don't know, the lowest number, I guess. So I'd say, well, 3 in the numerator, could I divide the denominator by 3 as well? And no, 4 is not a multiple of 3. Or you could go through the divisibility rules, right? You could say, well, is 3 and 4 divisible by 2? No, they're not both divisible by 2. Well, 4 is. Are they divisible by 5 or 10? No, they're not. Are they divisible by 3? Well, 3 is, but 4 is not, again, okay? So that eliminates most of them, and then we don't need to check any numbers above it, right? Like 7, 11, 13, or any of those weird ones. Which means that we've reached the end of writing our original fraction, 24 over 32, in its lowest terms, 3 over 4. Now, just going back to the beginning here, and I did that in, what was that, 3 different divisions, right? Where we divided by 2 in green, and then we divided by 2 in red, and then divided by 2 in purple in order to get the answer. Some of you noticed that 24 and 32 are both divisible by 8, right? They're both multiples of 8, which means that in the beginning, if you wanted to, and this is perfectly allowable, you could have said, well, I see they're both divisible by 8 because they're multiples of 8, and this would have taken care of all 3 of those steps in one step. And you would have had then 24 divided by 8 is 3, 32 divided by 8 is 4. And see how we get the same exact fraction that we did over here? So the process, while it's using the same method, it's dividing by different values, which kind of condenses all of this division over here into one full division problem. So that's why sometimes it may be beneficial just to stop and look at the numbers and think, especially if you have your, again, this goes back to the multiplication tables. If you have your multiplication tables down, you can look at a problem like this and want to really and think to yourself, what are these common multiples for a specific value, or even if you need to for now, just have the multiplication table chart in front of you, and just see. Well, I see 24 and 32 in line for 8. I know they're multiples of 4 as well, so you could have said, well, and again, I'm trying not to confuse you in this process, but 24 over 32, you could have done it in 2 steps. You could have said, look, hey, I'm going to divide this by 4 first, because I know they're both multiples of 4, and that would be fine. 24 divided by 4 is 6, and 32 divided by 4 is 8. And then you would have had this red step right there at 6/8, and then divided it by 2 to still get the same exact fraction. So again, I'm just pointing out that whatever you choose to divide by in the beginning, always check to see if its simplified form can be further reduced. If it can't, then that's fine, like the 3/4. But if it can, continue to reduce those until you find a numerator and denominator that can no longer be reduced. Now, again, I'm going to do this one twice. I'm going to do it with um, just using lower numbers first. So we may have to reduce this more than once. We will, actually. But then I'll show you that you can do it in one step. Again, if you just stop right now to analyze, if 45 and 63 are multiples of bigger values than the divisibility rules that we're going to be using, and just seeing if it is, because they are, by the way. But again, it's not required that you use those bigger values. You can do it in many steps if it's necessary. Yes, we do want this in lowest terms. So I would look at 45 and 63, and again, I would start with divisibility rules like 2, because 2, again, it's just a visual check. And for numbers to be divisible by 2, you have to analyze the ones place value. Now I got a 5 and a 3, both of which are odd. Or you could say both of these are, neither of them are multiples of 2. Both of them have to be multiples of 2, just the ones place values, in order for the full number to be divisible by 2. They are not. So I know these two values are not divisible by 2. So I would go then next to 5, which is, again, just a visual check. And I see, well, if it's divisible by 5, then in the ones place value, you would have to have either a 5 or a 0. Well, I have a 5 with 45 in the ones place value, but I do not have a 5 or 0 in the ones place value for 63, which means that this number is not divisible by 5. And it's not divisible by 10 either, because there's not a 0 or 5 in either of the ones place values either. So that brings us to the next most common value that we should check for divisibility rules, and that's 3. So in order for these two numbers to be divisible by 3, we take both values, such as the tens and ones place value, in this case 45 I'll start with, and all we're going to do is add these two values. If that number is divisible by 3, then 45 is divisible by 3, and I get 9. So 45, right now, when I add those two place values, I get 9 is divisible by 3, which means I know it is divisible by 3. But what about 63? Let's find out. So I take the 6 in the tens place value, the 3 in the ones place value. Let's add those together. Boom, we get 9. Okay? So that means both of these numbers are divisible by 3. So we got 45 divided by 3, and we'll take 63 and divide it by 3 as well. Now we haven't done the multiples of 3 up to 45 or 63, so I'm going to have to use long division to divide these. Okay? So I'm going to take 45. Let's go ahead and divide it by 3. 3 will go into 4 once. 1 times 3 is 3. Subtract 4 minus 3 is 1. That's in the tens place value, but drop the 5 in the ones place value. 3 will go into 15 5 times. 5 times 3 is 15. Subtract, you got 0 remaining. That's good. So the new numerator from simplifying this by dividing by 3 is 15. Well, what about 63? So 63 divided by 3. So 3 will go into 6 2 times. 2 times 3 is 6. That cancels the 6 out, just zeroes it out. So I drop the 3 in the ones place value. 3 will go into that 3 one time. 1 times 3 is 3, so we get a 0 remainder on that one. That's good. So that's my new denominator, 21. But we analyze this and we look, well, 15 and 21. Again, hopefully we have our 3's down that high. But you could add the two numbers as well. You could say, well, 1 plus 5, is that divisible by 3? And yeah, 6 is divisible by 3. And then you could take the 2 and the 1 from 21, add those together, which is 3, and that is divisible by 3 as well. That's a multiple of 3. So we can take 15 and divide it by 3, and also 21 and divide it by 3. 15 divided by 3 is 5, and 21 divided by 3 is 7. All right, now we have some unusual values, 5 and 7. Neither of these are further divisible by 3. Our original value was not divisible by 2, 5, or 10, so those are checked off. You could say, well, are they divisible by 4? No, they're not, because they weren't divisible by 2 in the first place. Are they divisible by 7? No, I mean the 7 is, but the 5 is not, okay? Which means that we have arrived at our answer. 5/7 is 45/63 in its fully simplified lowest terms. Now, I did say I'd do this twice, so let's look at the second method. Well, not method, but it's the same method, just dividing first by bigger values. Okay, so 45 and 63. We should know that these are multiples of 9, right? 9 times 5 is 45, 9 times 7 is 63. We also found that using the divisibility rules with 9, I don't use that as much because, again, we should have these multiples down at least that high. So just from some quick analysis on this, we could have noticed that 4 plus 5 was 9 and 6 plus 3 was 9, which means that these two numbers are also divisible by 9. But also, just memorizing our times tables, right? I can see that 45 and 63 are both multiples of 9. So that means that I could have divided both in the beginning by 9 and gotten my answer pretty quick. 45 divided by 9 is 5, and 63 divided by 9 is 7. Which again we see is the same exact answer that we got up here in purple, 5/7. So again, this one's a little faster. It may be a lot faster, especially if you have to use long division like this. It may be a lot faster, but there's a little bit more heavy lifting there at the beginning where you have to stop and think. And again, the amount of time this takes depends on the person. It may take you a long time to really figure that out. Again, if you have your times tables in front of you, I think that's a good practice, especially in the beginning. And you'd see in the row or column for 9s, you'd have 45 and 63, which means both of these are divisible by 9. Or you can do what we did in the first way here, and again, a lot of the lifting is in between the 45/63 and 5/7, where you got to use some long division there. So it really depends on what you feel more comfortable with. If you feel more comfortable doing the long division, do it. But if you feel more comfortable, and you do feel comfortable doing some analysis in the beginning, do that as well. The way that we did this one and the previous problem is generally the most common method, but it doesn't have to be the most convenient method for you. All right. We do have a second method that we're going to go over, but just so you understand, this is the most common method that is used in most of the math classes when we look at reducing or simplifying fractions into lowest terms. Now there is a third method, but we can't cover that in this class. You got to wait until like 9:50 to do that method. But right now we're looking at a second method. So our first method, of course, was looking at divisibility rules and applying division to the fractions just based on what we could see and know from the divisibility rules. But prime factorization is the second method. And again, this is why we've gone over prime factorization. We've seen it before, well, quite a bit actually. You can use prime factorization to take the numbers and write them as a result of all of its prime factors, okay? And there's a reason for this, which I'm going to show you here in a moment. But this takes us back. We're going to be using the factor tree to take the numbers and change them into their prime factorization. Okay, so simplified fraction or reduced fraction is where the numerator and denominator do not have any common factors to simplify with. This is important, especially when we look at prime factorization. If they don't have any common factors in the numerator and denominator, we consider it fully simplified. And again, we'll demonstrate that in this next example. So if you prefer that first method that we showed, then the second method really you should just ignore, right? This prime factorization stuff. But again, we need to be looking for its prime factorization for both the numerator and the denominator. Now I'm going to start with 54 right here like this. And I need to take the 54 and split it up into two other factors. So 54, there's several different values you could use, well, at least 3 or 4. I'm actually thinking of 6 and 9 on this one. 6 times 9 is 54. You could have used 2 and 27. That would have been okay. Now 6 and 9, neither of these are prime, but I know I can split these up further. 6, for example, can be 2 times 3, both of which are prime. And 9 can split up into 3 and 3, both of which are prime. All right? So I have the full prime factorization, right? I've come to the end of each of these branches of this factor tree because each of the ends are circled. Now we're going to come back to that here in a moment, but before I do, let's look at the prime factorization also for 144. And I think this tree is going to be a little bit bigger, and that's okay. So 144, let's see if I can split this up decently. So 144, I can see that it's divisible by 2, right? Now, again, there's several other values you could use, but I'm going to use 2 just to point out that if you need to use some long division from your divisibility rules, that's fine. 2 won't go into 1, but it will go into 14 7 times. 7 times 2 is 14. That cancels out the 14. Drop your 4 from the ones place value. 2 goes into 4 twice. 2 times 2 is 4, and that gives us 0 remaining. So the other factor there would be 72. And then you can take the 2 and the ones place value, and you could say, well, 72 I see is also divisible by 2. So you can do the long division here if you'd like. 2 will go into 7 3 times. 3 times 2 is 6. So we subtract that and get 1 left over. Drop the 2 in the ones place value to make that 12. 2 will go into 12 6 times. That'll give us nothing remaining. So I got 2 multiplied by 36 to get us the 2 factors of 72. Now I'm not going to continue this with 2's, although you could. I think it'd be more convenient in this case. You could use 4 and 9, but in my mind I was thinking 6 and 6 right here. 6 times 6 is 36. You could have used 2 and 18, but again, that it would just make the problem longer, that's all. So 6 splits up into 2 and 3, which means this 6 also splits up into 2 and 3. Okay? So I've reached the end of each of these branches. I got a 2, 2, 2, 3, 2, and a 3. So I'm going to rewrite this fraction, but where the numerator and denominator, I've used prime factorization or found their prime factorization. I'm going to show these as the product of their prime factors. So 54, for example, was 2 times 3 times 3, right? That's what we got down here at the bottom left. So I'm just showing its prime factors multiplied together. In purple, we had the 144, which is 2 times 2 times 2. Then I got the 3, 2, and 3 right there, times 3 times 2 times 3. Okay? Now, like we saw in that last slide, all we're looking for at this point are matches in the numerator and denominator. If they match, then here's what happens. Okay, so I see a match right here with 2 and 2. So I'm gonna show this on the side here. Let's isolate this 2 over 2. Okay. Well, what is anything divided by itself, which is really what this is? Anything divided by itself is 1. Okay? So 2 divided by 2 then becomes 1 right there. And so if I were to rewrite this, and I'm doing more work than you'd ever need to do on a problem on this one, but I just want to demonstrate what is actually happening, okay? So now, before I draw that black line, I'm going to show the 1 out here in the front. Okay, so what I have left over from the rest of the factors is 3 times 3 times 3 in the numerator in red, and in the denominator I have 2 times 2 times 3 times 2 times 3, right? And I've already talked about this before, but if you multiply anything by 1 here, which is what we have in green, it is itself. That is the phantom 1 property for multiplication. So I get rid of it. Now in the past, when you've seen this before, teachers often use the word cancel out. This has been canceled out. Well, cancel indicates that it just goes away completely. It's still there. The 1 is still there. 1 times this stuff, it's still there. Okay, so I don't want to use the word cancellation so that you understand that there's still a 1 there. You just can't see it, which is why phantom numbers are so creepy. But it's there. It's watching. It's lurking in the shadows, and we don't want it to get us, but it's just a phantom 1. Okay, phantom 1 is still there. So that's what we're doing when we're crossing these out this way. And so again, that's why we're looking for matches. So I see I have this 3, which I can match with this 3 right here that I crossed out in green. That becomes a phantom 1, so I no longer need those there. It is possible, if you prefer, just to completely erase these as well, okay? Because they're now phantom 1s. But you can also do it with another set of 3s, right? And it doesn't matter which 3 you use. I'm going to use these ones on the end. These ones we crossed out in orange. So those now become phantom values. So let's go and erase that garbage. And what do we have left? Well, we got a 3 in the numerator and then 2 times 2 times 2 in the denominator, right? So I'm going to rewrite this. Again, I'm doing far more work than you'd ever need to on an assignment or test. But now, in the numerator, I have the red 3, and in the denominator, I have 2 times 2 times 2. I just kind of compressed that. But again, I'm not showing any matches in the numerator and or denominator, which means that to fully simplify this, we just need to actually perform any multiplication that still remains. There's none in the numerator, it's just a 3 right there. But in the denominator, I have 2 times 2, which is 4, and then multiply that by 2 to get 8. So our new denominator is 8. And this is our final answer right here, 3/8, or 3 over 8. Now, if you looked at this also, you could have seen that 54 is divisible, and 144, by the way. Both of those, if we use the previous method, 54 and 144, I'm going to do it just with one division on this. But if you wanted to do it in one step with some analysis, maybe a lot of analysis, then you would find that this would have been divisible by, both of these would have been divisible by 18. Again, it's not important that you know that, but they are. And so then you would have had 3/8 right there. Okay, and you would have gotten the same answer. Of course, you could have divided by 2, which is what this did, and then 3, and then 3, if you use the previous method on this one to still get 3/8. Okay? So my final point on this problem is that it doesn't matter which method you choose. You can choose prime factorization, although it is less common, which should not be a factor for you in determining if you're going to use it or not. I'm just pointing out that it's less used, okay? Or you could use the previous method where you find that it's a multiple of specific values, or it's divisible by certain values. That method is also valid. So on this one, still want the fraction in lowest terms. We see this as an improper fraction to start with, which means we should end with a improper fraction as well. It's improper because the numerator, the 27, is bigger than the denominator, which is 21. So we look at 27 and 21, right? And I want to reduce this using prime factors, although you wouldn't need to if you didn't want to. You could use the first method, right, where you find that these two numbers are divisible by a certain value, whatever. Okay, but I'm using prime factors. So I look at 27 first. I want to make my factor tree. Yeah, the 27, though, the factor tree here, I know 27 is a multiple of 9. Okay, you could have said that it's a multiple of 3 as well, because 9 times 3 is 27. In either case, 3 is prime. And then 9 factors into 3 and 3 as well. Okay, so that's as far as we can take this tree, which also means that 27, and I'll do this one at a time, but we just found 27 is 3 times 3 times 3. All right, so I have that multiplication right there, the factors, the prime factors of 27. Let's look at 21 now. So I'm going to split 21 up. I know it's divisible by 3, and that would be 3 times 7. 3 is prime, 7 is prime, so as it turns out, that's the only two factors of 21 anyways. So 21 has factors of 3 and 7. Okay? So when I reduce this, when I simplify it, or make this in lowest terms, I just need any prime factors that match in the numerator and also the denominator. And yep, I got this 3 and this 3. Generally, when I do this, and especially if they line up like this, I will actually cross these out. And I'm not just crossing these out randomly. This is a 1 right there. See how I kind of made a 1 right there? Which indicates that we are looking, actually, at a phantom 1. Okay? So, this then changes the fraction into 3 times 3 over 7. And yes, there are no other matches in the numerator in red or the denominator in purple to make phantom 1s. So, to write our final answer on this one, we just need to do any multiplication that remains. So the 7 in the denominator is just going to stay 7. There was nothing to multiply with it there. But in the numerator, I got 3 times 3, which is 9. And yes, this is an improper fraction, which is kind of what it told us was going to happen anyways. But yeah, there we go. Prime factorization. That's it's a good method. I like it when I look at big numbers and I have to do this by hand, which kind of brings up the third method, though you'll discover that more in 950 or any of your future classes, really. So let's write 28 over 20 in lowest terms as well. Okay. So let's write it as a fraction though, and it should look like this, more like this on homework or wherever we're looking at this. And so we just look for anything we can divide 28 and 20 by to reduce it. Okay, because we are reducing, we're lowering these values, so we should be looking to use division. The question is, what should we divide these two values by? Now, there's several we can choose from. 2 would be the first one that comes to mind, but the second one is 4. I know that 20 and 28 are multiples of 4, so I know they're both divisible by 4. And so I would say, well, look, we got 28 divided by 4, which is 7, and 20 divided by 4, which is 5. Now, that actually thought there would be another division. With this, there isn't. So this is 7 over 5, and neither of these can be simplified or divided by the same value without getting decimals or fractions in that. So that is actually our final improper fraction for this problem. All right, division by 1. Anything divided by 1 is itself. We have seen that already. We've seen this slide actually already when we went over division from module 2. But in any case, yeah, anything divided by 1 is itself. So when we see a fraction like this, when it says divided by 1 is itself, we're looking at the denominator specifically. If you see a 1 in the denominator, you just pretty much write the numerator out. And it is possible that you can have 1 over 1. Doesn't matter, whatever the numerator is, that would be your final quotient. And again, notice that just like we saw in the homework, these are not written as fractions any longer. Like 7 over 1, we just write it as 7. Well, this one, it's kind of like you got that phantom divide by 1 right there, but what we've done essentially is make that a phantom divide by 1. Okay? So it's still there. It's still lurking in the shadows, which, I don't know, math is already scary enough as it is, but there we go. I showed it. Either way, it doesn't matter. So I didn't make a lot of examples for divide by 1 because We've seen this rule before, and I hope that you have that down pretty well, but we see divide by 1 right here. Again, it's the 1 in the denominator specifically. So I write my answer as just the numerator, whatever it is, and in this case, it is 13. Boom. I like these problems, dividing by 1, or by itself, by the way, because it's pretty quick, and eventually you'll get to the same point I am, where it's like, oh, it's just instinct. You see the 1 in the denominator, boom, your answer is the numerator, no matter what it is. Eventually, when you get into the more algebraic structures of things, then you'll just like, even if it was a letter there, it wouldn't matter. All right, fractions and base tens. If the numerator and denominator end in 0 digits, no matter how many zeros there are, you can cancel matching zeros in the numerator and denominator. We've seen this before, and I think we've seen it before with fraction form as well, although we weren't in the fractions unit. Now, again, this is going to create phantom zeros. I'm not going to go into how it becomes phantom zeros. We partially went into that before. Well, I guess I could say that it does have to do not necessarily with prime factorization, but factors of 10 for this, okay? So in this example, here's what this is saying, okay? Is that any zeros on the end of these digits, numbers, can be canceled with zeros in the denominator. And I use the word canceled. I'm trying to do that cautiously. But again, it's not that it's canceling away, that it's going away completely. It's just becoming phantom values. Now, this is going to change the problem, just like we've seen before, hopefully into something smaller, more manageable for us. Okay, so I would say I got these zeros on the ends here. Those will become phantom ones. These zeros that I've crossed out in red also become phantom ones. And these zeros I've crossed out in green would become phantom ones. And same with the zeros I just crossed out in orange. Those become phantom ones. So then what do I got? I have 8,400, right? I had 2 zeros that were not canceled or that became phantom ones. And I'm dividing this by 2. Now at this point you could use prime factorization, but prime factorization, sometimes it becomes not as convenient when you're looking at bigger numbers like this one, especially where the denominator is a small number, like 2. So to find our final answer on this one, I would just take 8,400 and actually just divide it by 2, the denominator. Okay, so I see I got 8, 2 will go into 8 rather, 4 times. 4 times 2 is 8, so that zeroes out the thousands place value. Let's drop the 4 in the hundreds place value. 2 will go into 4 2 times. 2 times 4 is, well, 4. So that becomes a 0. Now I got the 0 in the tens place value. 2 will go into that 0 0 times. If I drop it, the 0 in the ones place value to make it 2 zeros, it still goes into 2 zeros 0 times. So just like we've seen before with the examples we've done already, is this now becomes, it's no longer a fraction because I had nothing remaining on this, right? 0 remaining. It's just 4,200. Okay. Now, if I did have a remainder, I would probably look for values that I could divide these two up by. And this one you could have seen, well, we got the 0 in the ones place value, the 2 in the ones place value, so I know they're both divisible by 2. That's another way to do it. It's just you end up with 4,200 over 1, but we don't want over 1 fractions. We just want the numerator if we see divide by 1. So our final answer, 4,200. But you see how just getting rid of those zeros created a problem that was much easier to do, much more manageable for us to solve, even with this long division like this. Although, if you had done the original division, you would have had the same exact answer either way. So equivalent fractions, these are also known as proportions, but that's for something later. Fractions can be written in different ways without changing the value. This is exactly what we're talking about right here. We want you to be able to show fractions in using different values, but without changing the value. Let me rephrase that. Let me see if I can do it better on that one, okay? We want you to be able to show fractions with different numbers, but maintain its value. It needs to have equal value, right? So we can find equal value fraction by multiplying or dividing the numerator and denominator by the same number. That's true. Okay. Now remember, we use multiplication to scale these fractions upwards, or to make the numbers bigger. We use division to make them smaller. But again, we should not see any decimals or fractions within these fractions. So whatever you do, don't worry about using those right now. You pretty much never will. Okay. So it says find an equivalent fraction for 7/8. And when we do this, it didn't say anything specific about finding an equivalent fraction. We just want any equivalent fraction. That's it. Maybe there should be a y next to that and right there. You know what I'm saying? Like right there. Find any equivalent fraction for 7/8. Whatever. But we only want one. So maybe this is good. So I got 7/8. Now you can scale it however you want. I'm going to use multiplication, and I'm gonna use multiplication for me. That's easy. You can choose whatever multiplication you want. So for me, I would say I'm just going to multiply these by 2, and that's pretty easy multiplication for me. You may not feel comfortable with that yet, but we hope you will in the future. So that's going to change my numerator, right? I got 7 times 2, which is 14, and then 8 times 2, which is 16. Okay, and that is an or any equivalent fraction with 7/8. Another common way to do this, when it does not want a specific value in the numerator or denominator, a very common equivalent fraction, we don't want to multiply by 1, but I can make it 10, right? We know multiplying by 10, the only thing that's going to change is that you're going to end up with the same values, 7 and 8, but with zeros on the end. And that's okay. All right. So what I have in red here, 14/16, and what I have in blue, they're equivalent fractions, but again, they're looking very different on this. Even the 7/8 and the 14/16, they look different, but if you looked at value alone, they have exactly the same value, and that's what we're looking for on this stuff. There we go. Find any equivalent fraction to 5/6. Oh, okay. Yeah, we can do that. All right, now you get to scale it however you want. And again, 2 and 10 are very common values to use when scaling these fractions. I'm going to use something just a little different though. Although it's another common value to use when we scale fractions, just kind of offhand anyways, randomly. 5 is a pretty common value. So, but again, remember when we are scaling these fractions, we're finding any equivalent fraction to an original fraction. That when you whatever you multiply in either the numerator or denominator, you got to multiply in the denominator and numerator respectively. It's got to be the same. Yeah, so I am just choosing these values randomly, and you get to choose whatever values you want when you're scaling these fractions this way. But again, I'm trying to use something that's a little bit easy to work with, like 5, 2, and 10. So let's go and do the multiplication. Then in the numerator, I got 5 times 5, which is 25. And in the denominator, 6 times 5 is 30. So this is the fraction I get by scaling this fraction by multiplying the numerator and denominator by 5. But keep in mind that it didn't say anything specific about that denominator or numerator, which means there's an infinite number of values you could have used, such as 10/12 or 15/18 or 20/24. We did 25/30. I'll do one more. What the heck? 30/36, like this. Okay, and of course this pattern, some of you see the pattern within these, but this pattern continues. This one goes right there. Okay, but all of these fractions that I just wrote in green are equal to or have the same value as 25/30 or 5/6. See, now we're looking at an example where it says, hey, we want you to use a specific value. In this one, it's in the denominator, right? So we're looking at our original fraction of 1/9, and we want to scale it into a fraction that has a denominator of 18, right? That's what it says right here, okay? We need a denominator of 18, but again, it has to be an equivalent fraction A common mistake at this point where we're just learning this stuff is students just say, well, 1 right there, okay? Yeah, no, that's no good because it doesn't have the same exact value as 1 over 9. So we can't use 1 right here, right? So the question is, what value will go in that numerator? Well, we got to figure out what that value is. So the way this works, and we know we just scaled up, right? We went from 9 and turned it into 18, which means that we had to use multiplication to get there. 9 times something is 18. Now, some of you know what that is right now, and that's okay if you do. Which if you did, you could multiply it by the 1 right now as well. Okay, so you'd multiply the 1 by that value, and then you'd have your new numerator. I'm going to go through this in a little bit different way, just for those of you that may be struggling a little bit still, okay? Remember that all I'm really focused on right now, and this is the nice thing about fractions, is they kind of split problems up into 2 separate problems. What I'm really looking at is 9 times something equals 18. This is a fact family problem in order for me to figure out what that missing value is if you need it. Okay, again, some of you would know this one right away, and that's fine. But if I change this into a division problem, the 18 product becomes the dividend, and I can divide it by either of the factors. I choose 9, and that would be the unknown. 18 divided by 9, I know, is 2, which means 9 times 2 is 18. So this was scaled up by a factor of 2. 9 times 2 is 18, which means if I multiply the 9 by 2 in the denominator, I got to multiply the 1 by 2 in the numerator to get my new numerator 2. Now this one said enter a fraction that is equivalent to 1/9 with a denominator of 18. That means the final answer here that you would need to type in for the assignment is actually 2/18. It's not just the 2. It didn't ask what the numerator is, and it may. I'm not saying that it won't. I don't remember seeing it, but it could ask you if the denominator is 18, what would the numerator be? In that case, it's 2. This one asks for the fraction, so we write the full fraction as 2/18. Now, I use the fact family. Again, that should be familiar at this point, and I hope it wasn't too confusing. If it was, you're welcome to sit there, and again, let's take some analysis on your part, which may take some time. But you could think, well, 9 times what is 18? Because that's not too difficult of a multiplication table, right? And hopefully it wouldn't take you that long. If it does, that's fine, as long as you come up with that answer of 2. So here's another example where it's asking for a specific, oh, this one's a numerator. I kind of got caught off guard on that one. So we're taking the original fraction of 5/4 and we're going to scale it into a fraction where the numerator this time, it's a numerator of 40. So I got a 40 in the top value right there, the numerator. So we look at this one and we say, 5 times what is 40, right? Because we're going to multiply the 4 in the denominator by the same value. And yes, this is an improper fraction. That's not a problem. But 5 times what is 40? Again, you could change this into its fact family, taking the product 40 and dividing it by the factor of 5. And that will tell you what you would need to multiply the 5 by to get 40, which in this case is 8. 5 times 8 is 40. So to find the new denominator, 4 times the same 8 value, 4 times 8 is 32. So our final fraction with the specific numerator of 40 is 40 over 32. Now, of course, you're still welcome to write, because we shouldn't get any decimal values on these scales right here. So you could just, if you wanted to, you could say, well, I know I'm changing a 5 into 4 and multiplying it, so you could just write all your multiples of 5, if you don't have those memorized yet, and that's okay. But you'd see that 40 is the 8th multiple, so it's 5 times 8, then 4 times 8 in the denominator. So we want a equivalent fraction to 5/6, but with a numerator of 35. And again, this one is important to notice that it's a numerator of 35, because that'll be the top of the second fraction. So let's look at 5/6 right here like this. Okay, now we want something equivalent, so it should equal, and I'm putting some space between this so we can do some work. But this new fraction, we want a numerator of 35. So we have to start with the question of how do we change a 5 into 35? Now it is scaled up though, because we went from something smaller, 5, into something bigger, 35. So that means we are using multiplication on this, and we need to figure out 5 times what is 35, because once we figure out what that something is, then we can multiply the 6 by the same value and get the new denominator on this one. So this is where we kind of go back to our fact families on this one. So if I looked at just the numerators right here, I've got 5 times something equals 35. Now, if you have your 5 multiplication tables down well right now, you can solve this right now. But if you didn't, you'd have to change this using a fact family into a division problem. So you take our product, which then becomes the dividend, divided by one of the two factors. I choose 5, so we can do that direct calculation. 35 divided by 5 is 7. So I have 5 times 7 is 35, which means over here it's the same 7. 5 times 7 became that new numerator, the one that they wanted us to find specifically, of 35. But I need the denominator, so I take 7, which is how I scaled the 5, and I need to scale the 7 by the same factor of 7. 6 times 7 there is 42. And so this would be our new denominator. But again, on this one, it did want the full fraction, which would be 35 over 42. So fill in the blank to create an equivalent fraction. Okay, this is the same thing. It's just now they didn't tell us explicitly that it's 135 is the denominator. They just wrote the fraction for us. And this is a proportion. It's a proportion is when you have two fractions that are equal. So they have to have the same value, right? Now again, I'm gonna apply the fact family business on this one. I'm gonna say 5 times something is 135. How did I know to multiply? It's because we're moving in this direction. We're moving up, right? You'd have to say 5 is going to move up into 135, and since it's moved upwards, it must use multiplication on this. Okay, at least for now, anyways. So it's 5 times what is 135? Well, I don't have my 5 multiplications memorized up to 135, so let's look at its fact family with division. That would be the product 135 divided by one of the factors, I choose 5, equals the other factor, which is our unknown. That's what we need to multiply not only the 5 by, but the 7 as well. So I'm going to use some long division to figure this one out. 135 divided by 5. 5 won't go into 1, but it will go into 13 2 times. 2 times 5 is 10. Subtract, and you got 3 left over. Drop the 5 to make it 35. And 5 will go into 35 7 times. 7 times 5 is 35, and yes, we get a remainder of 0, which we should. So 135 divided by 5 is 27, and according to this fact family, then 5 times 27 is 135. So that means I'm going to take the 7 in the numerator and multiply it also by 27 in order to get the new numerator. So I'm going to show that work down here in the bottom left in green, 27 times 7. 7 times 7 is 49, carry the 4. 7 times 2 is 14, but plus the 4 makes that then 18. So that new numerator is 189. And I want to say that on the homework, this would be one of those where it's just got a box right here that you got to fill in. So in this case, you would just type in the 189. If it asks specifically for the full fraction, then you'd be looking at, well, the full fraction, 189 over 135. Well, let's go into comparing these fractions then. We're just looking at less than or greater than symbols right here, perhaps some equal to, I suppose. But in order to compare fractions, what we really want to do is make the denominators the same, which may take some work on that. And this goes back to, I think it was 3.2, where we were looking at lowest common multiples. Okay. Now, when we're comparing fractions, just like I said before, when we operate with fractions, which we will eventually do, finding the lowest common multiple is not as it's It's effective, it's just not necessary in order to do that. So on this one, we're looking for denominators and we're looking for common multiples, although they do not have to be the lowest common multiples. And again, that's because denominators indicate the size of the pieces. And once we get those sizes the same, then we can just compare the numerators, which one's bigger, which one's smaller. So that's why it says make the denominators the same and then compare those numerators, which tells you how many of those size pieces there are. Because the size is now the same, it is a direct comparison. That's correct. Okay, but again, they have to be the same. The denominators have to be the same. So we look at an example like this one and we say, well, I need those denominators to be the same, right? So I know I'm going to change these two fractions and then I can compare them, but I need the denominators to be the same. So we can look at the two different denominators. I'm going to start with 11, and I just need to find any other multiples of 11, right? Like 22, then 33, then 44, then 55, and 66 rather. Excuse me. So I'm gonna keep that way, and I've shown my multiples of 11, the first 6 anyways, but I need to show multiples of 2 as well. So 2, 4, 6, 8, 10, 12. We just barely missed 11. Let's keep going and see if we can find one of these multiples of 2 that's going to match one of the multiples of 11, okay? 14, 16, 18. I know not everyone needs this, by the way, but I'm going to be using it. So there's 22, and I've already seen 22, right? This 22 in red matches the 22 in green right there. So if I use denominators of 22, then I can compare these numerators directly across. But again, the question is, well, how did I get those two denominators? Well, I took the 11 and I multiplied it by 2 to get this 22 right here, right? So that means I would scale this fraction by multiplying the numerator also by 2. And 6 times 2 is 12. Now what you're going to see is that I'm going to scale the 1 over 2 by a different value. Okay, even though I scaled this fraction by 2, I do not need to scale this other fraction by 2 as well. In fact, 22 there is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11th multiple of 2. So that means I would have to multiply the 2 by 11 to get 22. So I'll have to multiply the numerator 1 by 11 as well to get 11. So now that my denominators are the same, I can compare just the numerators at this point, 12 and 11, and I see that, 12 is bigger than 11. 12 is greater than 11, which means that back in our original fractions, 6/11 is greater than 1/2. And yes, this would be a box or some kind of drop-down menu that you would choose. And once those denominators are the same, we're comparing the same size values, so we just compare the number of pieces that remain, which is the numerator. All right, that's pretty good. Let's go ahead and do this one as well. All right. You know what? I'll apply that same method that we just did on that last one. So, I would probably start with the bigger of the two numbers, though you don't have to. So I'm just going to look at multiples of 3, 3, 6, 9, 12, 15, 18. I don't know why it's slanting. 21, 24, 27, 30, 33, 36. Just the first 12 multiples for now. Let's see if that's good enough. Let's look at multiples of 10, 10, 20, 30, 40, 50, 60, 70. Okay, that's fine. Because I know that I already have a matching multiple, and that for me is 30 right there. 30 in red, 30 in purple, even though my 3 kind of is garbage right there. So we look and we see, what do we have to multiply these values by? The denominators specifically, what do we got to multiply them by to get those new denominators, which should be then denominators of 30? Well, the 3, that is the 10th multiple, so it's 3 times 10. So I can take the numerator, 2, and multiply it by 10, which gives me the new numerator. Now I'm going to emphasize this before I continue. 20 over 30 is exactly the same value as 2 over 3. It's the same exact value, just like whatever I get out of 7/10, and this new fraction here, um, it will have an equal value there. So we took the 10, you'd have to multiply that by 3. So I'm going to take the 7 and multiply it by 3 as well to get 21. And so now I'm just strictly comparing the numerators, 20 and 21. And I see that 21 is bigger, so 20 is less than 21, which means this should be eating the 7/10 in the beginning. So 2/3, this would read 2/3 is less than 7/10, which is true. Now there is a shortcut to all this, especially when we're just comparing fractions, two fractions like this, okay? What you can do, and this does not require you to find multiples, because there's a quick way to find common multiples. It may not be the lowest common multiple always, but again, we don't care if it's the lowest common multiple. We just need a common multiple. And to do that, all I do is I take the denominator from one of the fractions, such as this one, the 6 in red, and I multiply it by the denominator in the other fraction right there. See that? 5 times 6 there makes that 30. But once again, if I do that to the denominator, I must do it to the numerator as well. The numerator there is 3, so 3 times 6 is 18. Okay, and this, again, this guarantees a common denominator, although it may not be the lowest common denominator. So I take now the first denominator, which was 5, I'll make that purple, and it's going to give me a new fraction, and I multiply the 5 in that fraction by the denominator of the other fraction. See, 6 times 5 there is going to give us 30 in purple right there. But once again, I need to scale the full fraction, so I need to multiply the 2 also by 5. 2 times 5 is 10. And now that my denominators are the same, it really is a matter of just ignoring them because it's the same size pieces. But I see that 18 pieces is more than 10 of those same size pieces. So this reads 18 is greater than 10. So going back to the original fraction, 3/5 is greater than 2/6. More. So keep in mind, I mean, 5 and 6, that's pretty nice right there. They're low numbers, but remember, especially if these are bigger, more ugly numbers, like 13 and 27, for example, right? If we had 13 and 27, I think the multiplication is a more direct, more convenient method to work with because it will give us a common denominator, no matter how ugly it may be, but it'll be the same. That's what we need. And then you just got to figure out your corresponding numerators for both of those fractions. So while it may not be so uh, practical to use this method with lower numbers like this, I think it becomes very, very practical once we see more ugly numbers like I was saying, 13, anything beyond 13 really.